Welcome back to this mini course on modeling and simulations of machine component systems. This is the third part, and in this case I will discuss lumped models. My name is Roland Larsson. I'm professor at Division of Machine Elements, Luleå University of Technology in Sweden. I will try to talk about types of models. This is probably not a complete list of types of models, but I will mention these types. I will talk about deterministic, stochastic, and black box models. I will discuss discrete or continuous models, and I will discuss linear or nonlinear models. If we start with the question about deterministic and stochastic and black box, we start with the deterministic case. In that case, there are physical laws to be established, like the force equilibrium, for example, and flow balance. Hooke's law, you remember from solid mechanics, and a typical example is the cantilever beam, like this one. It's a typical case where we can compute the deflection of the beam if we apply a force, for example, in the end here. We have plenty of deterministic laws in mechanical engineering. Another type could be stochastic, and I call them stochastic because they are more like probability elements or random elements. We don't really know the physics, or it's too complex. And I took an example of bearing fatigue life that's maybe more realistic. If we want to have a model where the risk of fatigue failure of the bearing should be involved, we just know some kind of probability that fatigue failure occurs. We have a big problem to model it deterministically, to try to model it exact for each case. And the third one is the black box, and in that case I think it is, I mean it's more lookup tables and it's regression analysis. That means that you don't, also in this case, you don't really know the model, but you have, for example, in experiments, you have been able to run experiments, and you have measured output data from that, and you make your curve fit, or more advanced, you use some kind of artificial neural network, or you simply just use a lookup table. If you have the input data here, you know that type of output data will come out. So, but what's inside here is not known. That's the reason why it's called black box. In this case, I will mainly talk about deterministic, or only talk about deterministic models. Then to the question continuous or lumped. A continuous model, that means that we have back to the cantilever beam here again. In that case, we have a very large number of degrees of freedom, or maybe in the real case we have an infinite number of degrees of freedoms, but with some different numerical techniques like the finite element model, we can we have a finite number of elements, but probably pretty many elements here. But as you may know, you may take this, this is a linear elastic. If we assume it is a linear elastic material, and then there is a simple relationship between the force and the deflection here, and 1 degree of freedom, only 1 degree of freedom instead of maybe hundreds here in the finite element model, can mimic the same thing. It can mimic the deflection in the point here in the end of the cantilever. It can also we can by good accuracy compute the first eigenfrequency of the system, for example, by only using 1 degree of freedom. So And in that case we call it lumped models. So it's a very much a simplification, but pretty good in many cases. So for a cantilever beam of this type, it's definitely a good approximation. If we are just interested in the force deflection relationship here, there is no point actually in having the full beam here. The full beam model will of course give you the stresses in different positions. It will give you the deflections in different positions. But if we are only interested in the end position here, then a lump model is good enough. And there are plenty of different lump models, and I will show you a few of them. And for example, the mass and spring, that's a typical lump model, and you can also add damper. Friction, I used friction as a lump model. It's a typical relationship between the normal force and the friction force. If we have sliding friction, there is at least some kind of approximation that you use a friction coefficient. A Hertz contact, since I'm working myself pretty much with tribological problems, I often face problems where a spherical ball, for example, meets a flat surface like this. And in that case you can find the force deflection curve by using something called the Hertz contact theory. And that's also a 1 degree model. A flow capillary restriction is yet another one. So if you know you have a flow here, and you have a pressure here, you have a capillary here, capillary restriction here, you know that the pressure drop will be of a certain level. And so there is a relationship between flow and pressure in that case. We'll come back to that in next part. And here's an example where we have the possibility to make a lumped model. And this is a typical machine component system example also, or even I called it mechatronic example here. So if I have an electric motor, I have a drive shaft, I have a pump, hydraulic pump. I pump fluid or hydraulic oil through a hose like this into a hydraulic cylinder, and when the oil is pumped in here, this will raise the cylinder and carry the applied force. So when I switch this motor on, the drive shaft will deflect a little bit, and it will start rotating the pump, and after some time some flow will occur here, and some pressure will be built up, pressure high enough to lift the force here. Here it's if you remember the previous part of this course, we talked about subsystems, and here it's pretty easy to define subsystems. So this is one, the drive shaft is another one, pump, hose, cylinder. So, and there are also inputs and outputs for the different components. If I go to next slide here, you can see for the electric motor, for example, we have in one end we have the voltage and current, and in the other hand we transform that voltage and current to torque and rotational speed. The drive shaft, that's more a mechanical component with torque and rotational speed in both ends. The pump transforms the torque and rotational speed to pressure and flow. The hose is like the drive shaft, it just transforms or transfers or transmits, maybe it's a better word, the pressure and the flow to the other end of the hose. Well, if you have a constant, a steady system operating under steady state conditions, the flow and the pressure may be, at least the flow will be the constant, while the pressure may drop a little bit due to resistance here. But especially when you have time-dependent problems, there might be other things that change the fluid, that the P and the Q are not the same as the P and the Q in the other end. And finally, in the hydraulic actuator, the P and the Q, the pressure and the flow that is coming in here, is transformed to force and speed of the hydraulic actuator. And all these subsystems, as you may see in here, there are two types of inputs outputs in both ends here. Some are connected to forces or to voltage, to torque or pressure force, while the other one is current, fluid flow, speed, rotational speed. And there is some kind of generalization made to show a system like this, that all systems have a number of effort parameters and flow parameters, and they have, say, one input effort and one output effort, one input flow and one output flow. And what's in and what's out, that's a little bit determined by the cause and effect. So if we go back to the system, the example here, we had the motor, we had the shaft, the pump, the hose, and the cylinder. What we actually know is that we don't know how much current the system needs, but we probably knows the voltage of the system. We connect this system to the power grid, then it has a certain voltage. So what we actually know is the applied force here and the voltage in the other end. The other parameters we don't really know. So when you have defined the subsystems, it's very much about finding expressions or relationships or mathematical equations that between the flow and effort parameters. So two are inputs and two are outputs normally. And in this case, when you have this number of subsystems or number of you need a number of equations, like you need a number of equations in a system of equations to determine the value of each unknown. In this case, there are 1, 2, 3, 4, 5 subsystems, and there are actually 1, 2, 3, 4, 5, 6 multiplied by 2, 12 different inputs and efforts and flows. But since we already know the input F here and we know the input U here, then we only need as many flows and efforts as the number of subsystems. So we need n efforts and n flows. In this case, we need 10 relationships. We need 10 equations to be able to determine all the relationships here. We're not going to do that here. We can do that in some other example, but I just want to show you some typical, the typical effort and flow quantities. So we can talk about domains. And this is a funny thing here, or the good thing, that we don't distinguish between mechanics, hydraulics, electrics. They can be treated in the same way, or same syntax in some way, same way of thinking. So if we talk about translation, mechanical translation, then the effort is a force and the flow is a velocity. If we talk about rotation, then the effort is a torque and the flow is a rotational speed. If we talk about hydraulics or fluid mechanics, then the effort is a pressure and the flow is the fluid flow. And in electrics, the voltage is the effort and the current is the flow. And in general, there is a linear relationship. As long as we have linear models now, there are cases where the relation isn't linear, but in many cases, and we can be satisfied with linear relationships. Then there are actually three types of relationships between the flows and efforts, and we talk about resistive, inertial, and capacitive. Well, you recognize these names, don't you? Resistance, that's something we hear from electrics. Inertia, that's something we hear from mechanics. Capacity, that's also something from electrics. Can also be fluid mechanics. And we call these three different types of relationships these three different words. And the first one is the direct relationship between the effort and the flow. So it's just a linear model. It's just a constant that a proportionality constant between the two. A typical example is the relationship between the voltage and the current, and that's and then the proportionality constant is called resistance in this case. The inertial type of relationships are those between the effort and the first time derivative of the flow parameter. And then you have a typical example is the the force is equals the same as the mass multiplied by the acceleration, or mass multiplied by v dot, where the dot, you remember the dot denotes a time derivative. And finally, capacitive models, that's a constant multiplied by the integral of the flow parameter. And then the typical example is the force, the relationship between the force and deflection of a spring, and then the k is a kind of spring coefficient. So actually you could write it a little bit more complicated, but just to show you the idea with this, that there is a time derivative, time integral over the speed. That will give you the x in the end. So if it's an electrical, hydraulic, or mechanical system, doesn't matter. We can think about the systems in the same way. So starting with the mechanics, then it's a typical resistance is the damping, actually. So it's the damping is giving you resistance to motion, and normally linear damping means that the damping force is proportional to the speed of the. While the inertial is, of course, here is a special case. Oh, not a special case, but no, sorry, forget about that. It's straightforward. It's the v is the flow. But normally we express it in terms of x. So you can, again, it's an inertial relationship between the force and the speed, but we sometimes express it, or most often express it, as the mass multiplied by the acceleration. And finally, the capacitance, or the stiffness, is a constant multiplied by the integral of the speed, that's the x, so simply k multiplied by x, a spring coefficient. And you can do the same for the rotation, mechanical rotation, torque, rotation speed, torque, acceleration, torque, and deflection. And now we can start defining relationships for the different elements, and I'm pretty sure you have seen this type of relationships before. So if we have the shaft element, if we don't have any mass or inertia in this shaft, the relationship between the torque and the effort torque and the flow speed is simply like this, or in terms of deflection it looks like that, where the if we instead talk about that was a simple one, but if we make it a little bit more complex, then we use a spring mass element, which is very often used in mechanical lumped models, very not simplified but still useful models of mechanical systems. Then we normally talk about a spring with some mass. In this case, I lumped the mass of this could be the cantilever beam, it could be any mechanical system where we know the relationship between the force or deflection and the force. So I simply lump the mass in the two ends of that system. So if we connect some other system to this subsystem, we just lump the mass of this part to the end of this spring system. And now we have isolated this subsystem, we can just use Newton's second law to find the force equilibrium. So it's just the mass multiplied by the acceleration is the same as the applied forces. And here I also assume that we have some forces. Well, these are the forces that will be transmitted in some way. It's the same. So you do it for that mass and you do it for that mass. And again, F1, F2, X1, X2 are inputs and outputs, and you don't know which one is which until you have decided which way the flow of goes through the system. And of course, if this is a mechanical system, you should add mass to adjoining components too, if necessary, if they are rigid, or if they are assumed to be rigid, but they may move due to this the flexibility of the spring here, then you should add mass here too. It will require some thinking about how to do that, but it's you will learn by practicing this. The same thing can be done for the rotational shaft or a shaft element. Instead of deflection, we talk about torques and rotational angular deflection and rotational speed then. And the equations look the same, but of course there is a different K here, different spring stiffness in this case, because here is the torsional spring stiffness. So that's very briefly about mechanical lumped systems, or about models in general which we are using here. And in next part I will discuss hydraulic system lumped models. Thank you very much.